Cray, as you know, has a lot of expertise in the parallel vector processor market, and we've been building systems like that for about 30 years now. We also were the designers of the Cray T3E, which is a highly scalable machine based on microprocessors. So from the beginning of the project, the SV2 was designed to take the best attributes of both of those systems and combine them together. It turns out that vector processors actually allow you to build a highly scalable system and allow you to do many of the things we did with the T3E to make the system scale effectively. So powerful vector processors, a powerful interconnection network, and powerful memory subsystem combined with the features for effective scalability that we took from the T3E project were really all central assumptions of the SV2 design from the beginning.
We've got simulators that can simulate the characteristics of the system so we can validate our assumptions of how well the system is going to perform in different applications. The system architecture really achieves that. So there shouldn't be any surprises when the actual hardware powers up and how the applications are going to perform.
It will have processors that are as powerful as any other processor, in fact, much more powerful than most processors, and it will be the only machine that has a system architecture that allows you to profitably apply hundreds or thousands of those processors to the same problem. We took the opportunity with the SV2 project to start over with the instruction set and incorporate all of the research that we'd done, and also take advantage of the increased transistor density with more modern technologies to do many things to the instruction set. We increased the number of registers dramatically. We put in several features that we'd found would accelerate certain kernels or allow us to vectorize and parallelize constructs that we hadn't been able to do before. So the new instruction set gives us a big advantage over the traditional Cray instruction set, which we've been using for the past 20 or so years.
It opens up a lot of opportunities for software. One of the big opportunities is due to the fact that we have a very large register set. So in the past, for example, one of the challenges in generating good compiled code has been to manage register spills because we didn't have a lot of registers on previous generation machines. But with the SV2, we have ample registers, and this will allow us to generate a lot better code than we have in the past.
The most important thing we did was change to a distributed shared memory architecture, which realizes that there are physical constraints in the world and that you can't make all of memory in the machine equally close. So the machine is packaged with a shared logical memory, but that memory is physically packaged in a distributed way. So you have local memory that's closer to your processor. This allows you to get much higher bandwidth and lower latency to your local memory, which you can do as long as there's some locality in your applications, and there typically is. So we switched to a distributed shared memory architecture, which allowed us to scale the system up to hundreds or thousands of processors, which previous Cray vector systems had not been able to do. Yet we retained the high processor power, the high memory system bandwidth, and characteristics of the traditional Cray machines. If you take a microprocessor, it has an address translation mechanism, which is designed to convert the virtual addresses that the programmer uses into the real physical addresses of the machine. It has a translation mechanism that is sized to fit on your desktop or a server. When you try to build a system out of 1,000 processors, it just falls over because it can't keep enough information about the translations across the entire machine because the address space is too big. With the SV2, we did the same thing we did in the T3E, which is build a remote translation mechanism that allows each node to only have to keep track of its local translations and sends addresses across the machine using virtual addresses that are translated at the remote end. This is a scalable mechanism that is critical to making an effective kiloprocessor scale machine. There were also things in the coherence protocol or the communication protocol of the machine that we borrowed from the T3E design that allowed the machine to do explicit communication much more effectively than a traditional coherence protocol would do. So there were scalability features that were put into the design from the beginning. Also, if you want to coordinate 1,000 processors, you have to have a way to synchronize them very quickly. So the SV2 has special synchronization features that it can use to tightly coordinate the processors, both the local processors on a node, the single-stream processors within one of our multi-stream processor computational units and the processors across the entire machine. So there were special synchronization features that allowed you to coordinate the processors at a very tight level. We've done a number of things to the microarchitecture to allow the vector processor to better tolerate the latency that it will see in a large-scale distributed memory design. We've decoupled the scalar unit from the vector unit, so the scalar unit can run ahead doing the control instructions and issuing vector instructions. It can finish issuing the instructions for one loop, run ahead, and start doing the control and addressing for another loop. Meanwhile, the vector part of the processor lags behind and then does the computation on the data as it comes in from memory. This is called a decoupled architecture. It's decoupled both in terms of the scalar running ahead of the vector unit. It's also decoupled in terms of making the memory references and then going on and doing additional control work and then waiting till the data comes in before you do the computation. What this allows you to do is to keep the pipeline of requests to the memory subsystem full. Each one of the nodes of an SV2 has an integrated I/O controller that's actually comprised of 2 chips. These 2 I/O controller chips provide 4 high-speed I/O connections off of the node, which can be connected to the I/O subsystem or not, depending upon the I/O demands of the customer. So the I/O capability of the machine scales linearly with the number of processors. As you add on more processors to the machine, you naturally get more I/O capability. The building block of the SV2 is the multi-stream processor, or MSP. It's implemented on an 8-chip MCM, multi-chip module, and it includes 4 processor chips and 4 custom streaming cache chips. The 4 processor chips each provide a scalar processor and 2 vector pipes, and then the 4 processors share a high bandwidth streaming vector cache. And there are special synchronization primitives and wires between the 4 processors which allow them to be tightly coordinated and act either as 4 independent streams of computation or as one large stream of computation that has 8 vector pipes of performance. And then it has ports leading off to the memory subsystem on the board. If you take a look at a board, then it contains 4 multi-stream processors with a crossbar to a flat shared memory. The memory is controlled by 16 memory control chips. Each one of these has 8 direct RAM bus ports to a very high bandwidth memory subsystem. So you have a system building block that has 4 of our multi-stream processors and has flat, low latency shared access to the local node memory.
What I have here is an example of the multi-chip module package. 72 millimeters on the side. It's approximately 82 layers of glass ceramic. We have 8 ASICs on the MCM. We have 4 processor chips and 4 cache chips and approximately 180 decoupling capacitors on the top surface of the multi-chip module. We also have approximately 34,000 connections we make between the ICs and the multi-chip module on the top surface. On the bottom surface of the MCM is the approximately 3,800 connections we make between the MCM and the printed circuit board. So this is the technology that enables us to keep a very tight coupling between the processors and a very tight coupling between the processors and the first level cache. Because of the high power level of our MCMs, we needed a very local, very dense package for our DC to DC power converter. And so with, again, cooperation with a power supply vendor, we were able to get this package down to a very small size and have about 80% efficiency.
As you go to low voltage components, in the past when you used diodes to do the rectification in an asynchronous design, you have about a 0.6 volt drop across the diode. So right away the efficiency of your power supply is about 60%. By going to a synchronous design where we actually use MOSFETs to do the switching, we've improved our efficiency up to 80%.
So this was another key technology to achieve the kind of performance we're after and the kind of reliability we're after, where we mount these on the back of our printed circuit boards so that